Hello again. Okay, this is our second solving systems video, but this time we're going to solve by another method known as linear combination, or sometimes textbooks call it elimination. Before I solve it by linear combination, I'm going to try to solve it by graphing again. And I'm going to pick a very simple looking system. X plus y equals 7, x minus y equals 9, and some of you might even know the solution already because the coefficients are quite nice. So in slope-intercept form, I have y equals negative x plus 7 and y equals x minus 9. So for the first line, y-intercept 7, slope of negative 1, so it's going to be like this. And y equals x minus 9, y-intercept of negative 9, and a slope of 1, so like this. And I missed it by a little bit there. Okay, so it kind of looks like this is the point of intersection. It's below the x-axis, maybe negative 1, and the x-coordinate is maybe 7, maybe 8, or somewhere in between 7 and 8, not sure. If I'm told ahead of time it's integers, then I would guess it's 7, negative 1, or 8, negative 1. One of those pairs. If I'm not certain it's an integer, then I can't rely on graphing, as I said last time. So I'm going to use a second method to see if one of these two is correct or if it's neither of these. And that's called linear combination. Now, the idea behind linear combination is based on taking two equations and doing something with the two equations so you get one equation with one variable. We did that last time with substitution, but linear combination is a little more clean and orderly of a process. So first of all, here's the main idea. If I have two equations, a equals b and c equals d, then it is also true that a plus c equals b plus d. Why? Because all I've done is taken the first equation and added the same thing to both sides of it. Since c and d are equal, that's how I can say that I'm adding the same thing to both sides of the equation a equals b, and that's what it looks like. So I'm basically doing OPE. It's basically OPE here, because I'm adding the same thing to both sides. If that's true, then I can also take my two equations and do this. This is OPE again, in the form of subtraction, so SPE. This is APE, SPE. So since I'm subtracting the same exact thing, the same exact value from both sides of a equals b, this is legal. This equation is true, just as this equation is true, based on this pair of original equations. So this is the idea behind linear combination. You may take the two equations that you're given and add or subtract the two left sides and do the same thing on the right. Add or subtract the two right sides. Okay? If you do it, you must add left with left and right with right, or subtract left from left and right from right. You can't mix the addition and the subtraction, of course. Otherwise, you don't get a balance. So I'm going to do that with my little 2x2 system here. I'm going to take the two lefts and add them, and the two rights and add them, and see what I get. So if I take my two lefts, I get 2x plus 0y, because y plus negative y is 0. So I'm not going to write any y's. And on the right, I got 7 plus 9 is 16. So my x-coordinate is 8. And now that I know what x is, I just plug it in here, and I'll get y is negative 1. So now we see that it wasn't this point, it was this one right here. So my graph was not bad, though I wasn't sure it was an 8 or not. Okay, now I achieved that solution by adding the two equations. Let's see what happens if I subtract. I'll copy it down here. Now, I'm going to subtract, so I'm going to put my minus sign and put parentheses around the whole equation so I don't mess up any signs. X minus x, 0x, so no x's. Y minus negative y, 2y. 7 minus 9, negative 2. Divide both sides by 2. I get y is negative 1. I plug negative 1 in here, and I get x is 8. So whether I add or subtract it, both paths, adding and subtracting, took about the same amount of time to do. In this case, when I added, the y's disappeared, and when I subtracted, the x's disappeared. So that's the only difference. Now keep in mind that the coefficients here were both 1 and 1. The coefficients here were 1 and negative 1. If the coefficients had not been identical for the x's, when I subtracted, the x's would not have disappeared, of course. I would have had some number of x's here. In the same way, if the coefficients of the y's had not been 1 and negative 1, when I added, the y's would not have disappeared. So this is something very convenient about this system. Since we're not guaranteed that the two coefficients for x or the two coefficients for y will be the same, I have another example for you where the coefficients are not the same. Okay, so I have 2x minus 3y equals 3 and 3x plus y equals 2. As you can see, the coefficients for the x terms are not the same. Neither are the coefficients for the y terms. Okay, let's say I want the coefficients for the x's to be the same so that I can do my linear combination step and subtract so the x's disappear. Well, since the coefficients are 2 and 3, what I can do is find some multiple of 2, common multiple of 2 and 3, and then use OPE to multiply each equation by something to make them the same. The least common multiple of 2 and 3 is 6. So I can do something to the equation to make it so the x term turns into 6x for the first equation, as well as the second equation. If I multiply the first equation by 3, that'll accomplish the job. But remember, I have to multiply everything by 3. So the first equation turns into 6x minus 9y equals 9. The second equation, I can turn the x term into 6x if I multiply everything by 2. So that'll turn it into 6x plus 2y equals 4. Okay, now you can see the coefficients of the x terms are exactly the same, so I can subtract. 0x's, negative 9y minus 2y is negative 11y, and 9 minus 4 is 5. So y is negative 5 over 11. So already you can see that there is no way trying to solve this by graphing would have been easy, because there's no way I would have eyeballed that kind of coordinate on the coordinate plane. Okay, now I'm going to take my negative 5 11ths and plug it in one of my equations. I'm going to plug it in here. And multiply by 11 to get rid of the fraction. Seven. Oh. And x is 9 over 11. So my point of intersection is 9 over 11, comma, negative 5 over 11. Now, could I have solved this by eliminating y instead of x? Yes, I could have. So if I want to eliminate y, I look for the least common multiple of this coefficient, negative 3, and this coefficient, 1, and it would be 3, right? So I can multiply this equation by 3 and leave this one alone. So leave that equation as is, multiply the second one by 3, and then add. I'm not going to subtract here because this is a negative 3 and this is a positive 3. And then I get my x is 9 over 11 again, and I'm not going to plug it in now because you know what I'm going to get. Okay, so when you are doing linear combination, you have a choice. You can choose to get rid of the x's if that's more convenient, or you can choose to get rid of the y's. In fact, in this case, I think it was probably a little more convenient to get rid of the y's, because in this case, I only had to multiply the second equation by 3. I didn't have to do anything to the first equation. Up here, I had to multiply the first equation by 3 and the second equation by 2 to make the coefficients of x the same. So there's a little bit more work I had to do up here. Okay, so that's linear combination, also known as elimination.